Yeah, for those of you listening later on, we had a discussion on quantum mechanics before the start of, well, after the start of class. And today I'm going to finish up real fast nuclear chemistry and then start a review. So, and what you need to know, let me share the screen. So, and you guys can see my iPad, right? I'm not doing anything dumb. Tyler, can you see my iPad? Just making sure.
I can see it.
Okay, good. All things in the computer suggest that's true, but I just wanted to make sure so that I'm not just talking. You're like, what is he talking about? Okay, so what is on the final for nuclear chem? I'm not including mass defect. Mass defect is the E equals MC squared. I don't remember if I put it on the next test or not. I might have. I don't even remember if I put it on the next test or not. But the sources of radiation and the answer, most of the source of radiations are natural. Balancing nuclear equations, which is easy. The top numbers and the bottom numbers just have to be the same. And or find the identity of the nuclide. So, and like different types of radiation. So, but this is where we left off. We're talking about the different sources of radiation, and most typically it's natural. So, and we in Hawaii, we are not going to have very much, because we don't have very much radon gas, very little. And depending on where you're at, you can have more of that. So like the Midwest, for instance, there's more radon in the Midwest. It just depends on how much uranium and thorium is in the soil. So, I've never had more. I think the most I ever had is maybe 2 rem a year. So, because I told you that one time I had a CT scan, I was 1.7 rem just in that CT scan, which is kind of scary. But it's, I mean, if you look at the doses of things, I mean, you don't even feel anything till 20 rem. So we're allowed to get, like the civilian is allowed to get 5 rem. If you take a safety course in radiation, you're allowed to get 10 rem. You can get more dosage on your hands, for instance, because your hands, I mean, they're not vital. I mean, although I wouldn't want to damage them, right? But you're allowed to get higher doses on your extremities than your head or torso. So, and I think I told you guys I'm going to the dentist today, and I'm sure they'll take X-rays, and I always laugh at them because they always put they put that lead vest on you when they take the X-rays. It doesn't do anything. So because X-rays, they go in straight lines, right? So if they're looking at my teeth, like it means the X-rays, and it'll be like, imagine like a flashlight, it'll be a cone. The X-rays are going to be a cone coming out. It's not going to hit my chest if they're doing, unless they're shooting it this way or something like that. But they're always shooting, like, this way. And although what I don't object to is when they put I forget, my dentist does it, they put a collar around your neck. I don't object to that, because that does protect your neck and thyroid and stuff. So but I mean, when they put it on your chest and over your lap, I'm like, there's no way X-rays are going that way. But whatever makes them feel better. But X-rays though, and dental X-rays, they're going to be, so I'll get a little bit, and that's millirem. It's not very much. Oh, and it says skin dose. So, and I told you I'm going to the dentist. Back in the olden days, before my time even, there I'm an elderly person in his 40s. Dentists used to take their fingers and stick it in people's mouths and take the X-rays, and dentists had kind of manky looking hands because of that. And it was because of all the X-rays, the radiation caused damage. So that's one of the reasons why I think people didn't like dentists But I mean, I'm not excited about going to the dentist anyways. It's not like, yeah, I'm going to the dentist. I'm like, dentist. But it's more scary not to go to the dentist, right? Because then you can get your teeth. I mean, I'm happy to go to the dentist. It's a first world problem. But okay, so then let me talk a little bit about the radiation and radio tracers. And radioactive medicine is really fascinating. So I've had this one twice, the technetium-99. This is very common. Once it was injected into me. And the other one, I told you I ate a radioactive sandwich. So I was kind of scared. I was afraid that the radioactive sandwich would be delicious and I'd want to eat more of them, but it turned out it wasn't that great. So unfortunately, the technetium-99 is not going to be the new spice. The technetium-99M, the M means metastable. So when technetium is formed, it has an excited nucleus, and it's metastable, and it has a half-life of 6 hours, and it emits gamma radiation. And so when for most metals, when you put a metal in your body, well, metal other than the alkalis. So if you put most metals in your body, where your body sticks them is the bones. So with the exception of the alkalis, like I said, lithium, sodium, potassium, rubidium, cesium. So those just go everywhere. But any other metal tends to go to your bones. So you can image where your stuff, where bones are. And one of the reasons, the first time I got injected with it is I was injured playing football, and they wanted to see if I had stress fractures. And okay, this is not, that's a different uptake. But I mean, you would see something similar. So this looks like a technetium-99. So what can you tell about this patient? So first of all, you can see the largest signal is here. I should use a different color. The largest signal is here, and that's the bladder. So you get a lot of radiation there. And also, I mean, it looks like there might be something going on with this ankle. It's a little brighter than the other, but if you see there's certain things here, different growths. This looks like kidneys. So, and you can just see where there's more activity, more radiation. That's also where more things are being uptaken. So, meaning like if you have an injury to your bone, or if you have a cancer that's growing really rapidly, that area uses a lot of blood flow, uses a lot of nutrients. And if you get something that's a metal that kind of looks like calcium, your body's going to push stuff there, and then you'll see the signals there are going to be higher, and you'll get more gamma radiation there. So you can image certain things like growths, and or where if you have an injury, so where the repairing is happening. So like if the person had stress fractures, you would see activity, in a certain area if there was a stress fracture with technetium. So, and the other time I did is a stomach emptying study, right? I ate a sandwich, and then they had me stand up next to a detector every half an hour, and to see how long I had, then they imaged how quickly my stomach emptied. So, and it turns out I don't have gastroparesis, which a doctor thought I had. And thank goodness I don't have that. That's when your stomach doesn't empty as quickly. So, and although I should have brought this in, shoot. I have a Geiger counter at home, and when I left the hospital after the test, I was, like playing with it to see, I could find where in my GI tract where the technetium was with the Geiger counter, and also, when it was expelled, it wasn't there anymore, which is nice about radiation. It's really easy to see. So other radio tracer, iodine-131. So iodine, this is used for both treatment and for killing thyroids. So, and if anyone has to have your thyroid right here, it produces a compound called thyroxine, which is, it regulates your metabolism, your idle. And certain diseases besides cancer, there's Graves' disease, Hashimoto's disease. Those are autoimmune disorders. And you can in part observe them with iodine 131. Also, you can treat them with iodine 131. The treatment for it is to just destroy your thyroid and then take oral medications to replace it. So, and with iodine 131, if you have to have that procedure done, you have to go to an iodine-free diet. And what's interesting is almost everything that we eat has iodine in it. Like, so all of our salt usually has iodine in it. If you ever eat dairy, they use iodine to sterilize the udders of the cows. So there's iodine in dairy, and basically any dairy has iodine in it. So if you have to go on one of these diets, you're basically eating fruit and meat. So that's all you can really eat, and maybe some veggies, but no salt. And the idea is you get rid of all the iodine in your body, and then you uptake it. So in this, hopefully this is not an issue, but iodine 131 is also made from nuclear reactions. So nuclear weapons push out iodine 131. And in the event of a nuclear fallout, we have stockpiled iodine, potassium iodide tablets. And the idea with that is it'll saturate your thyroid with iodine. And then if your thyroid is full of iodine, it won't uptake any more iodine. So that's the purpose behind the pills, the anti-radiation pills. It only prevents, for radiation sickness, it only prevents things with your thyroid. So why don't I just take iodine pills all the time in case something happens with have a nuclear event? And the truth of the matter is, so iodine, it's one of those moderation arguments. If you have too little iodine, you get a condition called goiter, where your thyroid gland gets big. And if you have too much iodine, you get a condition called iodism, which is similar to lack of iodine in terms of symptoms. So, I mean, we shouldn't just be pounding iodine all the time. But the truth of the matter is we actually do just pound iodine all the time, right? Because if you ever eat fast food or processed food or, buy salt that's not kosher, if it's kosher salt, it doesn't have iodine in it, but sea salt has iodine in it. Regular salt, like the stuff you buy for $1 for a pound at the grocery store, that has iodine in it. Everything else, if you drink milk, if you eat cheese, ice cream, milkshakes, you're getting tons of iodine. So it's the effect on us is not that big a deal. Although if you look at Soviet USSR, the folks there, when you had the Chernobyl incidents, they didn't enrich their food like we do in the United States and always did. So there was much more issue with iodine for them. So other things, iron, you can look at your blood and spleen. So and thallium, you can look at your heart. Fluorine, that's for PET scans. You can use that. You can also use carbon for PET scans. You can use carbon 12 for PET. Phosphorus for just other stuff too. So PET is positron emission topography. So you can, here's a PET scan of a brain. You can see where there's different areas of activity, for instance. So this is great for radio tracers. So it means you can see inside the body without cutting it open, right? For me, they were able to tell how quickly my stomach emptied, and all I had to do was eat a sandwich and stand in front of a screen for 3 minutes every 30 minutes while I played, video games on my cell phone for the rest of the time, right? That's easy. They didn't even cut me open. I didn't even have to inject me with anything. I just had to eat a sandwich, right? that's how easy radioactive medicine is. And then it tells you if you have an issue, like a condition or not. So these are great. We also use them for civilian use, radio tracers. So like they put them in for flow. If there's a leak in a system somewhere, so like a pipeline. So if we like say, I mean, there's a huge amount of natural gas that runs between Alaska to the 48 states. And it's just a huge pipeline that goes across Canada. And so what would happen if we're saying, oh, we're missing some natural gas? Like, well, you know what we can do? We can put in some radioactive materials into it, some radioactive carbon, some carbon-14 or something like that in the pipeline, and just shoot it down. And all you gotta do is fly a helicopter or a drone or something like that with a Geiger counter. You're like, signal, 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 stop, no signal. I'm like, oh, that's weird. So over here, so somewhere here, we have a leak. And then you go like, all right, mark the location, send a crew kind of thing, spray soap on the side of it and look for bubbles. So that's an easy way to find leaks, is if you spray soap, and you can, like if you're thinking like your tire in your car is leaking somewhere, you can spray soap on it and put it underwater or something. Well, I guess they do it in the tire shop, they put it underwater, but you can spray soap on it and you can see if you see bubbles in a certain spot, that's where you know that the leak is. So I mean, that's so similar idea, you know, except with the body. So, and I said here so effects of instantaneous, that's not entirely true. And so it can be over time, instantaneous radiation exposure. Even you can get radiation sickness if you get 100 rem over a year. I mean, that's still possible, but it's going to hit you harder, of course, if it's fast, because it'll affect certain tissues, your stomach, your eyes, your hair. I think I said not in here, 60 rem, you can start to lose your hair. But I guess it's a horrible thing to think of, but if you start feeling, if you start throwing up within an hour of an exposure, you're probably not going to make it. So that's usually if you're ever really worried what a lethal dose is, if you have an event and then you start getting nauseous right away, usually that's a lethal dose. So you can use radiotherapy, and I sent you an article about radiotherapy. So, right, and this is a beam, putting beams and things. And the new technology, that's scary. I mean, that's not scary, it's awesome. I mean, you put a radio tracer like actinium into you, and it takes it to your cancer. So even before that, that's an incredible article. I love that article where they put the chelating agent with a receptor on it, and then they put a imager on it, so something like technetium or something, and they inject it in the patient's body, and like, oh, look at that, it all went to the cancer, you know, kind of thing. Like, oh, cool, if it all went to the cancer, well, let's do this now with actinium, and put in the cancer, and then the actinium alpha decays and completely destroys the cancer, and the patient's fine. Don't have to worry about chemo. Chemotherapy is horrible. Makes it feel, I've never had it, but people I know have had it, that makes them feel horrible. So heck, sign me up. I'd take that over chemo anytime. What else it can be used for? It can be used to sterilize food. So for instance, and I'm dealing with this issue right now. I like the sales at Costco when you can buy the 2 pounds of strawberries for $4. I did that this past weekend. I did buy some strawberries, and I've had to throw about 4 of them out because they're looking ugly like the top ones. So if you irradiate food, you can have it last longer. So it kills all the mold and other microorganisms to help sterilize it. So, although this is not typically done, to be honest with you, irradiation of food is an infrequent thing. Where they actually probably, the type of radiation they use is actually more ultraviolet than gamma or X-rays. Usually ultraviolet can be used to purify water, for instance. So, but yeah, Okay, I'm done with that. Anybody have any questions about nuclear stuff? Any questions? Usually have a no cool questions. All right, unfortunately. So I think I covered everything. Did I cover everything? Yes, I did. Unless you guys want to learn about nuclear weapons. It's not on the test. I shouldn't. I won't. I could talk about nuclear weapons, but you're probably more worried about passing the class than how nuclear weapons work. Okay, so what I want to spend the rest of the time today is prepping you for the final. So I went over and I looked some of the more difficult problems, and I thought I would review some of them. So the final is it's 50 questions, multiple choice. The questions aren't as hard. Like on the regular tests, I know I have multiple choice questions and I have word problems, and the word problems are kind of hard. I don't have word problems on the final. And not everything is like, I'm just kind of going this to kind of refresh your brains of sorts for the stuff that you had. And I mean, like, I can't cover everything in 2 hours, right? I mean, well, if I could, but I'd be speaking very quickly. So if you remember back in the first chapter, using the Clausius-Clapeyron equation. Normal boiling point of methanol at 64.6 degrees Celsius, heat of vaporization of 32.5 degrees Celsius. What's the vapor pressure of methanol at 12 degrees Celsius? So you have the Clausius-Clapeyron equation. And for me, I like to do the algebra first. So I would take e to both sides, and doing that would get rid of the natural log. And then you just multiply by P1. So is that too fast for you guys for the math? That's what if you rearrange it, so get rid of the natural logs by raising to the e power. I can even, and you would solve it that way. Now you just have to put in the right numbers. So normal vapor pressure, normal boiling point is going to be at 1 atmosphere. And to use this model, you have to use torr. So 760 torr times e to the minus delta h minus 35,200 joules by 8.314 joules per mole Kelvin times the quantity 1 over T2. It has to be in Kelvin, 285.2 minus 1 over the other one, 337.8. So yeah, so just make sure, and you can use the other way around. Just make sure that you're consistent. You can pick whichever one work for P1 or P2. It doesn't matter, just make sure you're consistent. Of course, the algebra is going to be different. So keep that in mind, but what you choose to be T2 versus T1 doesn't matter. So, and if you recall some of the hints here, this number here, this is a positive number, and which means you're going to have e to a negative number, which means if you put this in your calculator, you should get a number that's less than 760. So keep that in mind, you know, as you're doing the math. Did you actually want me to solve this, or do you want me to show you the setup, or what do you guys want? Is the setup fine, or do you want me to actually solve it and see the math? Yeah. So anybody there, Tyler, Kiana, do you guys want to see the actual math, or is the setup fine? Some of it I'll do the math. The next problem I'll do the math because it's a little more involved. But if you ever want, tell you what, if you ever want me to do the math, I mean, like the arithmetic, let me know. If not, I'm going to focus on the setup. So, okay, and students a lot of times, and remember, well, one of the reasons why I picked this problem here is because there's a lot of them that have natural logs and that kind of thing. It's not just a Clausius-Clapeyron, it's the Arrhenius equation and much of the other ones in the with natural logs and what do you call it, and thermo. I just wanted to have just say one, but also do it in the beginning in case you've forgotten everything. So, and mind you, there's only going to be like one problem or two problems on this, like what are the units of K or something like that.
Sorry, quick question.
Yeah, please.
Will these notes be available in the resources, or will you post the notes that we take today?
Yeah, I can send them out. You want me to send them out in an announcement?
Yes, please.
Yeah, or okay.
Thank you.
I shall do that. So this one I will show you a little bit more of the math. I mean, so you have this chemical reaction, and then you have these data. And there's two ways to solve it. You can look here, this one doubles, this one stays the same, and this one goes up by a factor of 4. So that means second order. So, and here, if you look, where is this? So, and if you look at the other one, this one stays the same, this one doubles, and this one times 1, that means M equals 0. So you can, if you want to do it in by inspection, that's fine. So, but usually if you want to do the more formal method, I guess I need to back up. When you look at this equation, and I'm just going to zoom in, here are the reactants. So you, as you're the chemistry apprentice, you go, okay, I have this chemical reaction. I need to figure out what the rate is. I'm just going to say the rate is equal to some rate constant times the concentration of some reactant raised to some power. I'm just going to call it N, and reaction of this, or the reactant of the second power, concentration of the reactant, and say raised to some other power M. You don't have to use N and M. You can use alpha and beta. It's whatever you know makes you feel special. So let me illustrate how you would then do it, and for that, so you use this rate law, and so the rate equals 0.0082 molars per second equals a rate constant, concentration of NO2 0.2 to the N power 0.1 to the M power. I guess I can, well, maybe I'll even drop these and put them in parentheses because I'll put the units. Molar, like so. So is everyone okay? What I've done there is I've taken the rate constant, that concentration, this concentration is right there, this concentration is right there. And then, of course, lots of arrows, right? So do you see where I've put all of those numbers? Okay. So same thing for then this one, 0.0021 molars per second equals same rate constant, 0.1 molar to the N, 0.1 molar to the M. I did the same thing. And now what I'm going to do, these are two equations, they're equivalent. I'm going to divide them. And you divide them, notice some things that happen. Units cancel, the K's cancel, this molar can, well, I'll show you later, right? This whole thing cancels there. So we're left with 0.0082 over 0.0021 equals 0.2 molar to the N, 0.1 molar to the N. And a couple other things, these molars are going to cancel in the middle there. So, and you can take this fraction. I always do this. I multiply by 1,000. I have 82 over 21 equals and 2 to the N. So, because 0.2 divided by 0.1, or you can 0.2 over 0.1 to the N equals 2 to the N. So then how do you get rid of the N? You take the natural log of both sides. Natural log of 82 over 21 equals N ln 2. Solve for N. So ln 82 over 21 divided by the natural log of 2 equals N. And what you'll find out, N equals 2. If you want to put it in like, actually, maybe I will put this one in the calculator just to show you. Am I going too slow for you guys, or are you liking the pace? Because I'm looking at the time. I'm only going to go through half of these. ln quantity 82 divided by 21 divided by natural log of 2. And this equals, if you have to put in your calculator, you get 1 point, ooh, and an ad for a better life. I did not realize that my life was that bad. Thank you, Google, for those wonderful ads. 5, 2, 3. So, I mean, if you put this in your calculator, this is what you get. But of course, within 2 sig figs, we have 2 sig figs. This number here actually is mathematically equivalent to 2 or 2.0. Right, so, okay. So we've got that. And similarly, so you can do that, and you also find out carbon monoxide is 0. So our rate is going to be equal to K NO2 squared. So second order. And then what do you do to figure out the rate constant? You pick any line. I can pick this line. So, and I apply that equation. So 0.0021 molars per second. So it's important putting the units in there. K times the concentration, 0.1 molar squared. So then you solve for K. K equals 0.0021 molars per second divided by 0.1 molar quantity squared. So this is going to be 0.21 1 over molar seconds. And we usually write it this way, 0.21 molar minus 1 second minus 1, like that. So 0.1 squared is, so if you wonder over the units for the dimensions, you have molar per second divided by molar squared, which is 1 over molar seconds, which is molar minus 1 second minus 1. If I'm doing the units too quickly. So the units are important. So that's the K right there then. And your rate law, if you wanted to write the whole rate law, rate would be 0.21 inverse molar, inverse seconds, concentration of NO2 squared. Yeah, question. Which one? Oh, no. Because you're dividing by 0.1 squared. So you multiply by 100. Right, so you get rid of, yeah. But thanks for checking on me. Yeah. No, but you when you divide by 0.1 squared, that's the same thing as multiplying by 100. So, other questions? Okay. And this is one of the ones, actually, if I had to pick any problem, usually these ones are the ones that students have the hardest time with of everything in the class, even harder than the calculus. Ooh, man, this is gonna be a hard one. Actually, I was thinking today as I was going into work, I'm like, I'm gonna be doing lots of math today. So this is using equilibrium. So, and specifically ice charts. So we have this chemical equation, 2 hydrogen sulfides in equilibrium with 2 hydrogens and sulfur. And we're given a Kc. And this is also a small Kc. And I picked this one because I use the X of small approximation. So, and it's just the initial concentration, is just with the words, the initial concentration is 0.025. So initially, so you write in what we know. Initially, we have 0.025 molar, nothing for this. So we have nothing there. So what's going to happen in this reaction? So it's going to shift right. We shift right towards the products, and we're going to lose 2 extent of reactions there. We're going to gain 2 extent of reactions here and extent of reaction here. And I'm getting this from the stoichiometry, right? So I'm getting the 2s and the 1s from the stoichiometry of the chemical reaction. And then equilibrium value, it's going to be 0.025 minus 2x. That's an ugly x. 2x and x. And then our Kc is going to be products, H2 squared over S2, or times S2 over H2S squared. So 1.67 times 10 to the minus 7 equals 2x squared x all over 0.025 minus 2x quantity squared. So, and this is the other thing I mentioned, students have a little bit of a hard time with this. You can approximate this by getting rid of that 2x, and you'd be left with 4x cubed over 0.025 squared. And then solving for x, you would get 1.67 times 10 to the minus 7 times 0.025, that's a 2, squared over 4. The cube root is equal to your x. Am I doing the algebra too fast? Do you want me to slow down the algebra? So, okay. So do that and you solve for x. And for this problem, then, I mean, depends on your concentration of hydrogen is going to be 2x. Concentration of S2 is going to be x. So whatever that is. So, and it's going to be a small number. So because of the equilibrium, it doesn't shift very far. It is a small number, this k. This k is a small number. Therefore, equilibrium does not shift very far to the right. So how do I square questions with this one? Is this helping you guys or? Okay. Remembering everything. I had a lot of sugar before class, so I'm feeling all the energy. Okay. And all this is not really like any math in this, but you know, get the hard problems wrong, not the easy ones. Le Chatelier's principle. These are the easy problems. So get these ones right. So Le Chatelier's principle, the equilibrium shifts to counteract the change. And again, if I had to pick anything for you to remember in this class, it's probably this one right here. And I always say left and right. Reactants are left, products are right. And the way you shift, if the amount of reactants increases, so too many reactants, the equilibrium shifts to get rid of the reactants. How does the system get rid of reactants? It forms more products. Too many reactants, you shift right. Too few reactants, or take away reactants, what happens? The reaction shifts towards the reactants, consumes, destroys the products to form more reactants. So you have the reaction shift left. So same thing with products. If you have increased the amount of products in the system, then what happens? There's too many products. How does the equilibrium shift? It gets rid of products, so it shifts left to form more reactants. If you remove the products, then what happens to the system? Well, the system shifts right to form more products. And things get a little weird. Well, let me go back before I talk about the pressures. For exothermic and endothermic. So exothermic heat is a product, endothermic heat is a reactant, and just treat that the same way. So an exothermic reaction, so heat is a product. If you add heat to an exothermic reaction, that's adding a product, you shift left. And if you take heat away from an exothermic reaction, that means you're taking away a product, shift right to form more products. Endothermic, if heat is a reactant, you add heat to a reactant, it shifts right because you added more reactants, you form more products. If you cool down an endothermic process or reaction, that means heat is a reactant. So if you lose reactant, you shift left and keep more reactants. But this probably makes sense though, even without the chemistry, right? So ice melting is an endothermic process. What happens if you lower the temperature in an ice melting process? Are you going to have more ice or you're going to melt more ice? The answer is you're going to have more ice, right? Because that should make sense to us, even not even knowing the chemistry, right? Colder things don't melt as fast than hotter things. So, all right, what about pressures? So if you have a system where you have more moles of gas on the reactant side than the product side, so think of the system, and if you increase the pressure of the system, so the system, and this is a closed system, so if I increase the pressure of the system is going to shift, is going to try and lower the pressure, which means it's going to shift towards the side that has fewer moles of gas. So for the top equation, so has 4 moles of gas, and the reactant side, 2 moles of gas, product side, increasing the pressure is going to shift it right. So because that's the lower moles of gas. So the system, you're putting pressure on the system. The system doesn't like the pressure, so it shifts toward the side that will release the pressure. Lowering the volume is the same thing as increasing the pressure, right? Because Boyle's law, pressure, volume are inversely proportional. So lowering the volume is the same thing as increasing the pressure. Look at the other equation there. So where you have 1 mole of gas on the reactant side, 2 moles of gas on the product side. If you increase the pressure, it shifts left. So it shifts towards the side of fewer moles of gas. Decreasing the volume is the same thing as increasing the pressure. It's the other way around. So let's go back to the top example. So what about decreasing the pressure? So it's like, so the system and like, in my pants on, I'm gonna tighten up my belt, you know, I'm gonna suck in my gut and tighten up my belt. What's gonna happen when, you know, I put on my sweatpants? My gut hangs out, right? I have this, I'm in a tight situation and my volume suddenly increases. What's gonna happen? I'm gonna fill that volume as much as I can. You go towards the side with the more moles of gas. So if the volume suddenly increases, it kind of like the system is kind of like, you know, doesn't tighten up the core anymore, lets the guts out kind of thing. You can look at it is this way: it lowers the pressure. The other, I use the same logic. Lowering the pressure means the system's going to try and fill that area with more pressure. It's going to shift towards the side with the more moles of gas. So lowering the pressure is the same thing as increasing the volume. So for lowering the pressure, left for the top equation, and for the bottom one, lowering the volume, lowering the pressure, increasing the volume is going to be shift right towards the side of more gases. So, and if you have a reaction that there's 2 moles of gas on both sides of the equation, or the same moles of gas on the other side of the equation, nothing happens with increasing, decreasing the volume. And also catalysts do nothing to equilibrium. It just increases the speed of reaction. It does not change the equilibrium. It really does change the equilibrium, but for this class, we say it doesn't. So of course it changes the equilibrium, but for this class, we say it doesn't. So, any questions? Another one that, so if salts are acidic or I know students have a hard time with this, and I just wanted to explain it. I'm trying to look at the problems that people get wrong. And also, as you know, the exam's gonna be open book, that kind of stuff. So determine if the solution form of each salt is going to be acidic or basic. So to do this, it helps to remember the strong bases. The strong bases are lithium, sodium, potassium, rubidium, cesium, and the strong bases, I'll go ahead and put it: beryllium, magnesium, calcium, strontium, barium. I'll put radon just to be fun. And I'll do francium, what the heck. The element named after France that only exists for a few seconds. So first 2 columns of the periodic table are the strong bases and the strong acids. The strong acids, they're going to be HCl, HBr, oops. HI, HNO3, HClO4, H2SO4, but the first hydrogen only. So, which means the counter ions of the strong acids, they're not going to react just like the strong bases. These ions are not going to react with water. So the question is this going to react with water? And for this part A, strontium chloride, in this case, you have a strong base plus a strong acid. And from this, you have a neutral salt. So, and the example I always gave with like the fighters, you know, like, I'm a strong base, I'm a strong acid, we fight and we defeat each other. and we have nothing left, and we have a neutral solution. So then here for B, we have a aluminum ion, which is a weak base. So we have a weak base, and we have a HBr strong acid. Even so, we have 3 strong acids. So I have a strong acid. So what's going to happen? It says, I'm a strong acid. I'm a weak base. A strong acid smacks you down. And we now have an acidic salt because I'm the strong acid, right? So this means it's going to be an acidic salt, acid salt. And the real reason is actually because the aluminum plus 3 ion plus, well, it's even more complicated than that. Plus 6 waters forms aluminum H2O6 plus 3, then aluminum H2O6 plus 3 is in equilibrium with aluminum H2O 5 OH complex plus 2 plus H plus or H3O plus with water. So that's the real reason, because it reacts with water. But in this case, it forms a complex. You don't have to know that it forms a complex, but you do have to know that aluminum hydroxide is a weak base, and a weak base and a strong acid forms an acidic salt. So then we have, methyl ammonium nitrate. So we have methyl ammonium nitrate, again, weak base, strong acid. In this case, again, we're going to have an acidic salt. And I'll change colors. For this one here, we have sodium, which is a strong base, and formate, which is a weak acid. How do I know that's a weak acid? Well, I've memorized my strong acids, and so HCHO2 is not one of those. So I know it, and it's formate, formic acid, but that's a weak acid. And when you have a strong base and a weak acid, it forms forms an alkaline salt. So strong base, weak acid, and same line. I don't know, again, the way I always remember it is like strong base, weak acid, fight. Grr. Strong base wins over weak acid. We have a basic salt. That's, I said, how I remember it. What really happens is sodium plus water, no reaction. So formate, see, forms formate will react with water, and the fact that the formate forms a hydroxide anion, then that's the reason why it makes it alkaline. So basic is because of the hydrolysis reaction. And sodium, of course, it's a counter ion from a strong base. It has no reaction with water. And for ammonium fluoride, we have a weak acid, a weak base. We don't know. And I'm not going to ask you that question on the test. So, because it's ambiguous. I mean, it's not ambiguous if you look up the value, the Ka value, but I don't want to do that to you. So the answer to this one is it's probably hydrofluoric acid because that tends to be the stronger acid than ammonia as a base. So questions with these at all? So, okay. Ooh, Henderson-Hasselbalch. If I'm going to have you remember two things in this class, I want you to remember Henderson-Hasselbalch because if you go on, especially for you bio folks, it seems most of the people here though are more physical and or engineering, but the bio folks, they need to use this quite a bit. So doing the pH, you can use the Henderson-Hasselbalch equation, which is the pH equals the pKa plus the log of the base of the acid. So for this one, the pKa is going to be minus log of the Ka, 6.5 times 10 to the minus 5, plus then the log in the base. Which one's the base? It's the one that has the alkali in front of it. It's usually alkali, like, you know, lithium, sodium, potassium. And for biological stuff, it's going to be sodium or potassium. So you could use calcium or magnesium, but the thing is with alkaline earths, they tend not to be as soluble. So the alkali metals are much more soluble. So you must almost always see alkalis for this. So the concentration of the base is 0.15 molar. And then the concentration of the acid. Which one's the acid? It says acid in the name, 0.05. And you just plug that in your calculator and get the pH. Does anybody want me to do further math on this, or is this adequate for you? Okay. So another hint with these, you can also do this equation as the pKa plus the log of moles base over moles acid. Like if you, for whatever reason, have something and they tell you mass or something like that, like, oh man, I gotta calculate the concentration. If you're given moles of something rather than mass, just or moles rather than concentration, just use the moles. Because concentration is moles per liter, and the concentration of the base is moles base per liter solution, and the concentration of the acid is moles acid per liter solution. 1/liter solutions cancel, and you're left with moles base over mole acid. So the moles don't cancel typically, unless they're the exact same number, then they cancel. But so you can't always assume the moles are going to cancel, but the volume will cancel in that equation. So time, okay. KSP, solubility product constants. Again, flying through the semester in warp speed. So when you have something dissolving, so like lead chloride is a sparingly soluble salt. So lead chloride, for instance, is a sparingly soluble salt, and your K is going to be the products, Pb plus 2 chloride squared over the concentration of PbCl2. So, right, but you get rid of the solids and equilibrium constants, and you're left with just the KSP, solubility product constant, is then going to be plus 2 Cl minus squared. So, okay, and you do this like other equilibrium expressions. Initial change equilibrium, we initially have 0. And your change minus solubility, oh, sorry, plus solubility, plus 2 solubilities. Equilibrium is going to be solubility and 2 solubilities. So our KSP is lead plus 2 Cl minus squared And the number is 1.17 times 10 to the minus 5 equals solubility times 2 solubility squared equals 4 solubility cubed. And that means then that solubility is equal to 1.17 times 10 to the minus 5 over 4 cube rooted. So, questions with that one? Okay. Non-standard reactions. So consider this reaction at 298 Kelvin. We have 2 nitrogen monoxides plus oxygen going to 2 nitrogen dioxides, all gases. And the standard free energy is negative 71.2 kilojoules per mole reaction. What is the standard, what is the Gibbs free energy under these non-standard conditions? So let's calculate it out. The delta G is equal to delta G0 plus RT ln of Q. Q is the reaction quotient. This is going to be products. So you can do pressure or whatever you want. Pressure NO2 squared over pressure NO squared pressure O2 to the first power. So put in the numbers. So delta G is going to be delta G0 minus 71. And I always write it out. Joules plus R, 8.314 joules per mole Kelvin, temperature 298 Kelvin, natural log of Q, pressure NO2, 2 squared over 0.1 squared 0.1. So, which that's going to be the natural log of 4,000. Okay. So, do you want me to keep on going or do you want me to stop there? What's that? Okay. So you solve for delta G and then compare it. The more negative means more spontaneous, so you compare it to the initial one. So that's how you set that one up though. Questions? Okay, so 4 minutes. I don't know if I can finish this one in 4 minutes. So, well, are there any topics that you want me to cover next class, last class? Anything that you are ever had a hard time with, you need to go over? Can anyone think of anything? Nope. If not, I will pick my own. I'll need to make more, and I'll send it out, Kiana, to everybody like I did last night, and I'll post the notes. So use this. Do I have time to start this? You know, I don't think I can finish this in 3 minutes. So I think I will pick up here. So yeah, I'll add some more in the next class as well. And so that way you're not, you know, but if anyone has any ideas or something you want to go over, you want me to go over, please feel free to email me. If not, I will pick my own topics, and I will also communicate with you the topics beforehand so that you don't have to, you know, like scramble to put your notes on. And I'll go ahead and send the notes today as well, so that you have reference to them as you study. So you'll get the completed notes next time as well. So, any questions? Yeah, go ahead. When is the final test due? That is May 13th. May 13th. May 13th is the final day for everything. I have to submit the grades soon after. So, yeah, I've been giving people extensions to, you know, like, I mean, it's just, I can't extend it past the end of the semester. It's like, then I've got to calculate grades and submit them. So, Tyler, do you have a question or are you just saying goodbye?
No, yeah, so for next class, can we go over the one where it was like the change in moles? Like when you're before, after, I don't know if that made sense.
Changing moles for what?
I'll email you which chapter it was. All right, let me try to find it.
Is this the kinetics? Like,
Yeah,
so like when you have, oh, so when you have the chemical reactions and then this species goes forward at this rate, and how does that compare to the other rates of the other things?
yeah, because there was one that was talking about before, after, before it, or before addition, after addition, and then
Or
yeah,
was it dealing with the Henderson Hasselbalch when you have like when you add acid and bases to things? Was that the one?
I'll try to find it and then I'll email you
Okay, sure.
what chapter it
Yeah.
was.
Yeah, I'll go over it. Yeah.
All right.
Okay. And anyone who's listening online later, if you want to submit me topics, you know, please do so soon so I can prep, you know, for everybody. So, well, but on the fly is fine too, you know, but it's just, it'll save time. But so always feel free to ask questions, you know. But anyways, all right, I'll stop. And I know I'm over time, so I will end. Oops. What am I doing? I'll stop recording.